This is a LabVIEW Beginner lesson where we make a heart rate monitor. This is lesson 4 where we add modularity and functionality. In lesson 4-6 we'll be adding manual pulse detection to our application. Currently we're using a simple get the frequency VI from LabVIEW, and it works quite well, but I know there is a better way of making it, but it's more complicated and it's not that much better. The reason we're adding it partially because we want a better peak detection, but also to show how easy it is to add extra functionality to an application like this. We have to add a new user event which sends its data, make a new interface on the GUI, and then we need a function which does the manual pulse detection. We start by making a type definition which contains the data we will need to change it. We'll need 3 things. We will need a boolean which turns it on or off, so we can have manual ? And then here we'll just add multiple text. When it's on, it's auto, and then when it's on, it's manual. And then we need to define what our top levels are. Our function will work by us setting the top and bottom value, where the top is where everything over means a peak has happened, everything below means that that's reset. This is to create a sort of hysteresis of our pulse. I'll go more into detail of how it functions later. We'll just call this pulse settings. Maybe I'll add something here later. And we'll use that same name for saving. So now that we have our cluster, we can start by making the user events. And we do that the exact same way as we always do. While we're here, we want to also define these values from the beginning, or at least we want to define that it should start in the auto way, in the old way, because then there is no settings needed. So what we need to do that is to go into initial state and add the pulse settings. And by default it's auto, but we can specify that. So we don't need to care about top and bottom as they are unknown. We could at a later date define them if they're very common. And then initial manual, no, we want auto. Now we need to go into close to fix this. We can now add this functionality to the GUI. So let's do that. We can use them as it is now or separately. For now I'll just use it as it is, as it's simpler, and maybe we'll add some changes later, then this will be updated here. But you could easily just drag them out and push them manually into the function. And then let's duplicate this waveform to pulse settings, all elements, so if any of the elements change it will update. And we'll need to change this one, delete here, and then place it in here. Now we have the sending in order. Anytime there's a change, we will do the sending. We'll also add the initial values here. This way we know we have the same initial values both on the acquisition and in the GUI. And that's everything we need to do in the GUI. Let's go to the processing. Here we need to make a receiver event. that takes the input and then places it in here. We can add the data to our typedef so it can store it and send it around. I like to have the user events at the bottom, so I'll just put these and trade them. There you go. We need to add the pull settings there and put them into the user event so it will show up here. And then when you put a cluster into user event, it usually splits them up like this. This can be annoying, and a way around this is to put it into another cluster, then it will come in the same way, because the user event automatically unbundles your cluster. But it's really not a big problem. We'll just manually push them in again. And now when someone sends the data, we'll be saving it in our loop data for later use. Because the use will actually be in here. We need to make a case where it either just does this thing or it does our other VI. So let's start by making the VI that can filter it manually. It will have the most similar inputs as the simple filter waveform, so I'll just reuse it for simplicity. Let's call it manual. And let's go about editing this. We will not have this one out. We will have the waveform in and then the frequency out. Because we can reuse this one. And we can reuse the input here. And so this will only replace this little bit here. Now it's getting messy. Okay. Let's go back to our manual heart rate. Add the double out. Frequency out. Waveform in. And let's change the icon before we forget that. Manual heart rate. Now we almost need to delete everything in here. We can keep a few things. So what we'll do is to use the data in with our top and bottom values to the frequency. So we'll need to add the top and bottom values too. Top, change to control, and then bottom. From these inputs, we will get the frequency out. But the question is how? What we need is some sort of mechanism which counts how many times the top crosses after the bottom has been reached. We can't just have one value because maybe it goes over it, goes under the top value again, and goes over it again, but this is just a ripple around our top value and does not indicate another heartbeat. So what we need is a bottom value, which kind of says if it's below this value, you can register top values again. What we're really measuring is peaks, but we want the peaks after they reach a certain bottom value. We need something that goes through every value, so we'll need some sort of loop which goes through every value of y and checks wherever it crosses the top value after it has reached the bottom value. So let's wire these up. Now with this one, it will iterate over every y value, since we have nothing connected here and this is the only array. First, we want to know, let's start at the beginning. We want to know when this has passed the top value. And when it has passed the top value, we get a true out here. But as I explained earlier, just having the top value means it could pass it multiple times without ever going down, and that would not indicate a heartbeat. So what we need to do is make this set some sort of flag. And we can do this by placing this, the output here when it's bigger, in here, which will set a flag high. And then we add the shift register that keeps this value up. And we can say it starts with this value at low. And now every time this passes over, it sets this to high, but it has no way of restarting it. So for every set of samples, we'll only get one heartbeat, which would be wrong. What we need is a way for this to be reset every time it crosses this value. And then we can just do the same. We'll add a comparator. So anytime this, the waveform value is lower than this, it sets this flag low again. So now, if this value is larger than this, then this will become true. Regardless, if this is true or false, it always becomes true. And the same for this one. Regardless of what value it is here, it will become false, low, when this value is lower than this value. And from here, we toggle this on and off. But we need some way of counting the toggles, because we don't want just one toggle. We want to have every time it flips from low to high. A way to do this is that to say if the last value was low, but it's now high, that means a heartbeat, or like it has a trigger. Because if this value is high and this is high, it means it has stayed over the value or not yet past the bottom value. And if this is low and this is low, it means that it has stayed below the top value both last and this time. The way to measure this would be to take an AND loop. So we'll say when this is high and when this is not high. So this will only trigger, as I previously stated, when this is low and this is high. This will only happen when this is being crossed. It will not happen when it's being crossed to the lower, because then it will be false here, and this will be high, and this will be true, and this will then be false. But now it will happen when this is false, which means that the previous was false, and this is high. Now we can enter when there has been a change. We also need to count this. And to do that, we'll just add another shift register, which is based on this, because as we know, this will only be true if there has been a transition. And we can add a value, 0 here, so it starts every time it's used at 0. But when it's true, it adds a value here. And when it's false, it will not add anything. And now we get how many times it has triggered, i.e. how many times the heart rate has passed a certain point. But this is not enough. We don't want the number here. We want this based on the frequency. But that's not enough, because if it happened 10 times over 10 seconds, it means the frequency is 1. But if it happens 10 times over 1 second, it means the frequency is 10. We need a way to calculate it from the sample size we're actually doing it over. So what we'll need to do is to multiply how many samples are here with the delta time. So what's happening here is that we will divide how many samples we are on the timing. Currently, by default, we have 10 seconds of data, and our timing is every milliseconds or 1000 hertz. So this will be 0.001. So we'll multiply 0.001 with 10,000. This will give out the value of 10, which means we will have this many peaks will be over 10 seconds. So if, say, we have 20 peaks over 10 seconds, we have 2 hertz, which would be 120 beats per second. But we'll do the calculation afterwards. Right now, we're just interested in the data. So then we'll put this here, and we'll do the conversion since we'll be calculating in double. What we need to do is to get the frequency, we say the peaks divided by how many seconds the peaks are over, and then we get the frequency. We'll just add this here. We call it peaks here for a lack of a better word, but something like a sine wave at 10 hertz would have 10 peaks in a second. Now we want to add it into the calculate waveform here. This is getting a bit messy. What we'll do is to cover this one in a case. Let's place this the function in here. And let's make a little bit more space. We have a lot of space. And we want this in here. And we put our waveform in here. We get our frequency out, which gets calculated, and then we need our extra functions. The manual there. So is it manual? True. Well, so we need to change these. So now that is it manual? No, false, then it does this automatic one. And if it's true, then it does our other one. Let's take it for a test now. It's automatically on the auto one, so we see that. Let's look at our waveform. It's this one we care about, because we're using the filter data, and we see it always crosses over 0.004. So let's add that, 0.04. And it always goes below, it seems to go below -4. There we saw a little bit jump over that. Let's change it. And now let's see how it works. You can see we get a little bit different data. It's hard to know with our random waveform generator. So what we could do to test this even better would be to go in here. What we could do to test it better is to go into our simulator and just cancel this one here, so we always get 60 hertz. Let's launch it up again. And here we say it's about 60 seconds. It's probably some jitter, some delay here. So it's not perfect. And now it seems like it stopped moving, but in actuality the waveform is so similar we can't really see it move. And let's see the tops. We see that the highest one here now is 0.02, and which includes everything. And we see the lower one, which includes everything, is 0.8. So we'll just add these numbers. 0.02 minus 0.08. And then add manual, and we see it works, but we can't really see it, so let's clear the waveform to see that the new waveform comes in. And we see it stays at 1. It was even more accurate from the beginning because this is a slightly improved one. But to show that it doesn't really work, if we say 0.04 where we drop 1, we will get a completely different result. 54 because it drops 1 peak, so it's 1 bit less. And that shows that our function works. And it has even more accuracy than the old one from the beginning, but also we have a bit more control. So in this lesson, we saw how to make a manual peak detector. The next lesson, part 5, we will make the GUI a little bit more pretty and we'll compile our code and make an installer.